Preparing for a multi-agent systems engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is a multi-agent system, and when is it preferable to a single-agent architecture? A multi-agent system divides a complex objective among autonomous components with distinct roles, tools, or expertise. I would choose it when tasks are naturally separable, require parallel work, or benefit from independent verification. For example, research, planning, coding, and review agents can collaborate on a software task. A single agent is often simpler and cheaper for straightforward workflows. The key trade-off is improved specialization versus coordination overhead, latency, observability, and more difficult failure handling. While answering, define agents, autonomy, communication, specialization, coordination, and task decomposition. Explain when parallelism, modularity, fault isolation, or heterogeneous expertise outweighs the additional orchestration and communication complexity. Question 2. How would you design the architecture for a production multi-agent system? I would separate the system into an ingress layer, orchestrator, agent runtime, tool gateway, state store, model gateway, and observability pipeline. The orchestrator assigns work and enforces budgets, while agents remain focused on bounded responsibilities. I would use durable workflow state, typed messages, idempotent tools, and correlation IDs for tracing. Model access should support fallback and rate limits. Finally, I would add policy checks and human approval for irreversible or high-risk actions. Make sure to cover user and task intake, orchestration, agent roles, shared or private state, tool execution, message transport, model gateways, persistence, observability, security boundaries, retries, and human approval points. Question 3. How do you choose between centralized orchestration and decentralized agent coordination? Centralized orchestration is easier to reason about because one supervisor owns planning, budgets, and termination. Decentralized coordination can improve resilience and scalability, especially when agents operate across domains or locations. I usually begin with a supervisor because predictable execution matters in production. If bottlenecks emerge, I introduce bounded peer collaboration or regional coordinators. The decision depends on coupling, latency, failure independence, and how much global context agents genuinely need. In your answer, compare global visibility, deterministic control, scalability, communication overhead, resilience, emergent behavior, consistency, and debugging. Mention when a supervisor, peer-to-peer protocol, or hybrid design is appropriate. Question 4. How would you design communication protocols between agents? I treat agent communication as an API contract rather than free-form chat. Each message should include a schema version, sender, recipient, task ID, correlation ID, deadline, priority, and explicit response type. Payloads should distinguish facts, requests, decisions, and errors. I prefer structured data for machine actions, with natural language only where useful for reasoning. Contracts need validation, backward compatibility, and idempotent handling so retries cannot duplicate side effects. Be sure to mention typed schemas, message identity, sender and recipient, correlation IDs, versioning, deadlines, priorities, acknowledgements, ID impotency, error responses, payload limits, and compatibility across agent implementations. Question 5. How do you prevent multi-agent systems from entering infinite loops or repeatedly delegating tasks? I never rely on the model to decide when collaboration should stop. The runtime enforces maximum steps, delegation depth, elapsed time, token usage, and tool calls. I assign each task a unique fingerprint, detect repeated states, and require measurable progress before allowing another iteration. A workflow state machine defines legal transitions and termination conditions. If progress stalls, the system cancels execution, returns a partial result, or escalates to a human. Focus on hop limits, recursion depth, task budgets, deadlines, duplicate detection, progress criteria, state machines, cycle detection, cancellation, escalation, and clear termination conditions enforced outside the language model. Question 6. What strategies would you use to manage shared state and agent memory? I separate ephemeral conversation context, durable workflow state, and long-term semantic memory. Agents should own specific fields where possible, while shared updates use typed events, optimistic concurrency, and version checks. Retrieved memories need provenance, timestamps, confidence, and access controls. I avoid placing the entire history in every prompt. Instead, I summarize and retrieve relevant slices. This reduces cost and contamination while preserving auditability and allowing controlled conflict resolution. Discuss short-term context, durable task state, semantic memory, transactional updates, ownership, consistency, conflict resolution, provenance, retention, privacy, and selective retrieval rather than indiscriminate context sharing. Question 7. How would you evaluate whether adding more agents improves system quality? I would compare the multi-agent design with a capable single-agent baseline using the same task set, tools, model budgets, and evaluation criteria. Metrics should include success rate, groundedness, tool accuracy, latency, cost, failure recovery, and human preference where necessary. I would run ablations removing agents or communication rounds to identify actual contributions. More agents are valuable only when quality gains exceed added cost, delay, coordination errors, and operational complexity. In your answer, cover task success, factuality, tool correctness, latency, cost, reliability, collaboration overhead, ablations, representative datasets, human judgments, and comparison against a strong single-agent baseline. Question 8. How do you handle disagreements between agents? I make disagreement explicit rather than forcing premature consensus. Each agent submits a conclusion, evidence, confidence, and assumptions. A critic or adjudicator then compares claims against trusted sources, tests, or tool outputs. Voting can help with independent opinions, but it fails when agents share the same bias. For high-impact decisions, I require stronger evidence or human review. The final record should preserve dissent and reasoning provenance for later analysis. Mention independent evidence, confidence calibration, role-specific expertise, critique and revision, voting limitations, arbitration, provenance, uncertainty, escalation thresholds, and avoiding correlated errors from identical models or prompts. Question 9. How would you prevent agents from producing plausible but incorrect information? I would ground factual claims in retrieved documents, databases, or executable tools rather than trusting generated text. Outputs should include citations, structured fields, and confidence, then pass schema and business rule validation. A separate verifier can check calculations, references, and contradictions. I also distinguish hypotheses from confirmed facts in the protocol. Evaluation must include adversarial and out-of-distribution cases, because fluent answers can conceal systematic errors. Cover retrieval grounding, tool verification, constrained outputs, source citations, cross-agent critique, confidence handling, schema validation, uncertainty expression, adversarial tests, and separating generated hypotheses from verified facts. Question 10. How do you secure tools used by autonomous agents? I place tools behind a policy enforcing gateway and give each agent the smallest possible capability set. Arguments are validated against schemas and allo lists, credentials remain outside prompts, and destructive operations require approval or stronger authentication. Code execution runs in an isolated sandbox with resource and network limits. Every call is logged with identity, intent, inputs, outputs, and outcome. I also treat retrieved content as untrusted because prompt injection can manipulate agent behavior. Be sure to discuss least privilege, scoped credentials, allo lists, argument validation, sandboxing, secret isolation, approval gates, audit logs, rate limits, network controls, and protection against prompt injection and data exfiltration. Question 11. What is your approach to prompt injection in a multi-agent workflow? I assume any web page, document, email, or tool result may contain adversarial instructions. The runtime labels external content as data, keeps system policies outside agent-controlled context, and validates proposed actions independently. Agents receive only necessary permissions, while sensitive tools require approval and parameter checks. Detection heuristics help, but they are not sufficient. I combine isolation, least privilege, output verification, audit trails, and safe failure rather than attempting perfect prompt filtering. Discuss trust boundaries, instruction and data separation, content sanitization, provenance labels, tool call policies, least privilege, independent validation, indirect injection, suspicious pattern detection, and human review for sensitive actions. Question 12. How would you optimize latency and cost in a multi-agent system? I first instrument each model call, tool call, queue wait, and coordination round to find the real bottleneck. Then I parallelize independent tasks, route simple work to smaller models, cache stable results, summarize context, and stop once sufficient evidence exists. Budgets should cover tokens, time, and tool calls per task. Asynchronous execution and streaming improve perceived latency. I would optimize against a quality cost frontier, not latency alone. Focus on parallel execution, model routing, caching, context reduction, batching, early stopping, token budgets, selective delegation, asynchronous messaging, streaming, timeout policies, and measuring quality cost trade-offs by workflow stage. Question 13. How do you design reliable retries and failure recovery for agent workflows? I classify failures before retrying. Network timeouts and temporary provider errors may use exponential backoff with jitter, while invalid arguments or policy violations should fail immediately. Every side-affecting tool needs an idempotency key, and durable checkpoints let the workflow resume from the last safe boundary. Circuit breakers protect dependencies, while dead letter queues isolate unrecoverable tasks. Recovery should preserve useful partial results and never blindly repeat irreversible actions. Mention transient versus permanent failures, exponential backoff, jitter, idempotency, durable checkpoints, compensation, dead letter handling, circuit breakers, fallback models, cancellation, and preserving partial results without repeating harmful actions. Question 14. How would you ensure reproducibility and debuggability in agent behavior? I version prompts, policies, model identifiers, tool schemas, routing logic, and datasets. Each run receives a trace ID and the system records inputs, outputs, state transitions, tool results, latency, and token usage with appropriate redaction. Deterministic settings help, but model behavior remains probabilistic, so replay should use captured dependencies or mocks. Checkpoints enable step-level inspection. Reproducibility is essential for debugging regressions, auditing decisions, and comparing experiments fairly. In your answer, include versioned prompts and models, deterministic settings where possible, random seeds, complete event traces, tool snapshots, input capture, state checkpoints, replay facilities, privacy controls, and evaluation metadata. Question 15. How would you design a planner-executor-critic pattern, and what are its limitations? The planner converts a goal into typed subtasks, executors perform them using approved tools, and a critic checks results against requirements and evidence. Feedback can trigger targeted replanning rather than restarting everything. I would cap revision rounds and require concrete failure signals. This pattern improves quality for complex work, but it adds latency and cost. A critic using the same model or context may reproduce the planner's mistake, so independent checks matter. Cover decomposition, execution, verification, feedback loops, shared task representations, stopping criteria, critic independence, error localization, parallelism, latency, cost, and the risk of critics sharing the planner's assumptions. Question 16. How would you manage context windows when many agents collaborate on a long-running task? I would keep canonical facts and workflow status in structured storage, not solely in prompts. Each agent receives a task-specific view containing relevant evidence, constraints, recent decisions, and unresolved questions. Older dialogue is hierarchically summarized, while original artifacts remain retrievable by identifier. I track timestamps and provenance so stale summaries can be refreshed. Context budgets are enforced per agent, preventing one verbose collaborator from consuming the entire system's token allowance. Discuss hierarchical summaries, retrieval, structured state, relevance filtering, compression, context ownership, token budgets, provenance preservation, stale information, and avoiding repeated inclusion of full conversation histories. Question 17. What observability would you build for a production multi-agent platform? I would create end-to-end traces linking user requests, workflow runs, agent turns, model calls, tool calls, and state changes. Metrics include success rate, completion time, queue depth, token cost, retries, delegation depth, policy blocks, and per-agent quality. Structured logs should capture decisions without exposing sensitive data. Dashboards need workflow-level and agent-level views, while alerts detect rising failures, runaway loops, cost spikes, or distribution shifts. Be sure to mention distributed tracing, agent and workflow metrics, structured logs, prompt and tool telemetry, queue depth, token cost, quality signals, error taxonomies, privacy-aware sampling, and alerting on behavioral anomalies. Question 18. How would you test a multi-agent system before deploying it? I test deterministic components with unit and contract tests, then use simulated agents and recorded traces for workflow behavior. Integration tests verify model, tool, storage, and messaging boundaries. Fault injection covers timeouts, malformed outputs, duplicate messages, unavailable tools, and conflicting state. I add adversarial tests for injection and privilege escalation, plus load tests for concurrency. Deployment should use offline regression suites, canaries, monitored thresholds, and a fast rollback path. Cover unit tests, contract tests, simulation, replay, integration tests, fault injection, adversarial security tests, load testing, offline evaluation, human review, regression suites, and staged rollout with rollback criteria. Question 19. How do you decide whether agents should share one model or use specialized models? A shared model simplifies operations, prompting, evaluation, and behavior consistency. Specialized models make sense when tasks differ sharply, such as lightweight classification alongside complex planning or domain-specific extraction. I would route based on task type, confidence, latency targets, and cost budgets, then validate outputs through common schemas. Specialized routing increases operational complexity and can create uneven quality. I would prove its value with controlled benchmarks rather than assuming more models means better results. In your answer, compare capability, latency, cost, context requirements, domain specialization, consistency, fine-tuning, routing complexity, evaluation burden, fallback behavior, and the risk of incompatible output quality. Question 20. Describe a multi-agent project you would build, and explain how you would measure its success. I would build a software incident assistant with investigator, log analysis, dependency, remediation, and communication agents. A supervisor would coordinate evidence collection, while a policy layer prevents unapproved production changes. Success means faster diagnosis, accurate root cause hypotheses, fewer false escalations, controlled cost, and zero unauthorized actions. I would compare it with the existing runbook process using historical incidents and live shadow mode. Human feedback and post-incident reviews would drive iteration. Make sure to cover the user problem, agent responsibilities, workflow boundaries, tools, safety controls, baseline, measurable success criteria, operational constraints, evaluation dataset, and lessons from failures or iteration. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.